This is lesson 17 on multiplexers. Now a multiplexer is a digital switch in which the output Y is either equal to A or B depending upon the value of this input S. S is called the control line, and if S is equal to 0, Y is the same as A, and if S is equal to 1, Y is the same as B. So we can make this truth table where here's S equals 0, so Y is the same as A. Here S is equal to 1, and so Y is the same as B. There are 4 ones in the output, so we can make a Carnot map, shown here. The values of 1 correspond to the minterms 0, 1, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 1. We draw the 2 circles, and we can write the logic equation for Y. Y is, from this one, not S and A, or S and B. So that's the logic equation for a 2-to-1 mux. From that logic equation we can draw the logic circuit. Y is not S ANDed with A, or S ANDed with B. Okay, now this is a 4-to-1 mux, and the 4-to-1 mux has 2 control lines, S1 and S0, and 4 inputs, and Y is connected to each of these. So for example, when S1 and S0 is 0, 0, it's the same as connecting Y to C0. Now of course there's no physical connection, there's not a wire here, there's just a bunch of gates in here which make the logic circuit such that Y is whatever C0 is if S1 and S0 are both 0, 0. If S1 and S0 is 0, 1, then it's just like connecting Y to C1. If it's a 1, 0, it's like connecting to C2. And if it's a 1, 1, it's like connecting to C3. Now it turns out we can make this 4-to-1 mux out of 2-to-1 muxes. Let's see how we can do that. Remember, this was the logic equation we had for a 2-to-1 mux. We got it from the Carnot map, but you can really see it from this truth table. Here, this sort of little minterm is just not S0, isn't it? So not S0 ANDed with A, whatever it comes in. If A is 0, this will be 0. If A is 1, then Y will be 1. So not S0 and A, or B and S0. So you can just see it from that truth table. Now if we take 3 of these 2-to-1 muxes and arrange them this way, where we connect S1 as the control line for this one and S0 to both of these, then this will make a 4-to-1 mux. We can see that. This is a 2-to-1 mux. The output is V. Here's the logic equation. Remember how it goes. V is going to be not S0 and C0, or S0 and C1. Then W, the output of this one, is going to be not S0 and C2, or S0 and C3. And the output Z, now the inputs are V and W, so this is just going to be not S1 and V, or S1 and W. So in this equation for Z, we can plug in for V, this equation. For W, plug in this one, and we'll just get this term. Here's V coming in here, here's W coming in here. And we can now multiply it out. Z is not S1 and not S0 and C0, or not S1 and S0 and C1, or S1 and not S0 and C2, or S1 and S0 and C3. So this is the equation for Z for a 4-to-1 mux. You can really see it from this truth table. where the min term, not S1 and not S0, is right here, and you just AND it with C0, the input, or this min term, not S1 and S0 and C1, or S1 and not S0 and C2, or S1 and S0 and C3. So there's the logic equation for a 4 to 1 mux. Finally, let's look how we can make a quad 2 to 1 mux. This is a 2 to 1 mux, that is a single control line. If S is 0, these 4 A's go to these 4 Y's. That is, Y3 is the same as A3, Y2 the same as A2, and so forth. Y0 the same as A0. And if S is 1, then the 4 B's go to the output Y. And you make it by 4 2 to 1 muxes, in which you have the same S control line going to all 4 of them, and then one of them has the inputs A0, B0, which goes to Y0, the second one, A1, B1, goes to Y1, third one, A2, B2, goes to Y2, and the third one, A3, B3, goes to Y3. So if S is 0, all the 4 A's go through and become the 4 Y's, and if S is 1, all the 4 B's go through and become the 4 Y's.